Honors Algebra 2, Chapter 2, Section 8, along with Section 5. So we'll start with Section 5 here. It's pretty quick. It's direct variation. So direct variation is just a linear equation, but it's when two variables vary directly by a constant of variation k. So we say that y varies directly with x. And so if you look at the form of the equation, you should recognize that y equals kx. You should recognize it as our slope-intercept form. It's just a very specific kind of slope-intercept form because it doesn't have a y-intercept here. So what is the slope in this? Our slope is just our k value. Our k value is the slope. It's the slope and how we relate the x to the y. And then what is the y-intercept? Our y-intercept is 0. So our 0 is our b value, our y-intercept. It's not stated there, so we can always just add 0, and the additive identity does not change the value. So when we write these equations, we are usually given a point. So a lot of times we're given the point, we see the relationship, and we have to find the actual k value, or the constant of variation. So write a direct variation given a point. So to do that, we have to do two steps here. We have to first find the constant of variation k. The k value we have to find. We're given the two, the x and the y values. We need to then find the k value. Then we can write the equation second. Write the equation using the variables x, y, and then whatever the constant of variation k would be. So example of that, a flower is 4.5 centimeters wide and has a leaf 7.2 centimeters long. And so we can write a model for the flower if the leaf length varies directly with the flower width. And so if we know that that relationship is always true, that we know there's a direct variation, then we can plug them in. We know that the length width varies directly with the flower width. When you write this though, the first statement here, the leaf length is actually what is the isolated variable. So the leaf length here equals our constant of variation times the flower width. And so the order in which these are written is also important. So here's how I'd write it with variables. Then I'm going to plug in our values we know. We know that the flower has a width of 4.5. Do not know k. And then we know that the length is 7.2. So then if we divide both by 4.5, we would actually find our k value. And so for this, we find our constant of variation, 1.6. And so our equation we can actually write then is our leaf equals 1.6 times the width. And so if I know the width of the flower, I can times it by 1.6 and I'll find the length of the leaf. So what would change if we reversed it and said that the flower width varies directly with the leaf length? If we did that, then we put the w first equals k times the leaf length. And we plug in the values. And so for a lot of these, you're given the two variables, and you have to first solve for the constant of variation k, and we plug in our 7.2, and so you're dividing by 7.2 now. If you do this, you'll find the constant of variation is 5/8 or 0.625, and so then the width is equal to 0.625 times the leaf length. And so you can think about it a few ways. You can think it's 5/8 of the leaf length, or you can say that it's 62.5% of its length. So you can say that a few different ways, but that would be the direct variation for that example. The other part of the lesson here is 2.8, which is graphing inequalities. And to do that, let's first quickly recall how to graph equations. We did that last night. And so we're graphing this is in slope-intercept form, so we should be able to state what our slope is, which is -2/3, although I don't have my x in here. I'm supposed to have an x right there. And our y-intercept b is 4. And so if I'm going to graph that, I first plot my y-intercept, 4. And I can use my rise over run. So my equation, or my fraction here is rise over run. So I'm going to go down 2, right 3, down 2, right 3, and then I can connect that. I know it's a linear equation, so that'd be good with those 3 points. I could go left 3, and then up 2, that would also work. And then here's that line. A second one we talked about here is this equation, the second equation, which is actually in standard form. So a fast way of graphing that is if I plug in 0 for x and 0 for y. So when I'm doing that, I'm trying to find my x-intercept. The x-intercept would be 20 divided by 2, the number in front of x, which is 10. And then the y-intercept is going to be 20 divided by the number in front of y, -5, and I get -4. Again, we can do that because the other term would be 0, because you plug 0 in for it. To find the x-intercept, y is always 0 for every x-intercept. That's why that works. So our x-intercept is 10, so on the x-axis, plot the point 10. Our y-intercept is -4. The y-axis, plot -4. And then we know it's a line, so we can just connect those 2 points. And there you go. And the last one here is not in a form, so we need to manipulate. Now I have a choice. I can add 5x to both sides, it puts it in the standard form, or I could divide by 3 to both sides like that and then simplify it. It doesn't matter which method you would prefer to use. I guess I'll use standard form here because that's one students usually need more practice with. So if I add 5x, I get 5x plus 3y equals 30. So then my x-intercept is going to be 10 or 30 divided by 5, so 6, and my y-intercept is going to be 10, 30 divided by 3. So y-intercept 10, x-intercept 6, so intersect right there, and then here's our line. So those are 3 lines from these 3 equations, and we've already done that. So we've already done it in lesson and homework. What we're talking about in 2.8 is really inequality. So if we graph all the ordered pairs, x, y, all the points, that satisfies this inequality. So x is less than 5. Where's x5 at? X is 5 here, but x is 5 here, and x is 5 here. X is 5 at any of these points. So all of those is equivalent to 5. Where's x less than 5 are all the points that are over here, left of it, left of that, of this kind of vertical line. So I know this is the region where it works, all the points. Now how do I graph all these points? I can't. There's an infinite amount of points. So we graph that by shading the side. We first want to draw the line though. This is less than here, so it cannot equal. So just if we had the open circle, we're going to draw a dotted line. So that represents it cannot be equivalent to. And then we're going to shade the side to the left of it. So these would be the solutions for that inequality. So graph the inequalities. These are kind of steps. You first want to graph the inequality as if it was an equation. So this vertical line here is like the x equals 5 line. Then you draw the line solid or dashed. It's solid if it's a less than or equal to, or if it's a greater than or equal to sign. Dashed if it's less than, or if it's greater than, use a dashed line. And then you want to test a point. Test a point to shade a half plane. So if the point is true, then you shade the same side. If the point is false, then you shade the opposite. So this last part, some students feel like you don't need to, they can just see an equation. But be careful, it's not always that clear. And so you need to take a point, put it into the inequality to figure out if that point is true or false. Does it make the inequality true or false? And so then if it's same or opposite, is because if it's true or false. If the point is true, it's the same side you shade. If the point is false, it's the opposite side you shade. So examples. So first we're going to graph the equation. So if I just graph this equation, it's in slope-intercept form. So -5, up 2, right 3, 2, right 3, up 2, right 3. You can do this many times as you need to graph our line. But before I graph our line, I want to think about it. because it's a greater than symbol, so I want it to be dashed or dotted. So put arrows on the other side, on both ends, and then I need to shade a side. So if I choose a point, now what point do you want to choose? It doesn't matter. You can choose whatever point you want. I typically try to choose the point 0, 0 whenever possible. The only time you cannot choose 0, 0 is when the line goes through that point. You can choose any point you want except for the points on the line, because we want to test the two sides. So if I put 0 in for y and 0 in for x, and I evaluate that, I get 0 is greater than -5. So is 0 bigger than -5? Yeah, that's true. Because that's true, then I'm going to shade the same side as that point. The same side, because that point is true, it needs to be in the shaded region. Okay, so the other one here, so we can have standard form here. We can graph the x-intercept here. 12 divided by 2 is 6. Y-intercept, 12 divided by 3 is 4. So let's plot those. 4, 6. Now because it's an or equal to, I can just graph the actual line. And then we need to shade a side. So for this I need to test a point. I want to test the point 0, 0. If I plug 0 in for x, 0 for y, I get 2 times 0, which is 0, plus 3 times 0, which is 0. So we get 0 is less than or equal to 12, which again that's true. So I'm shading the same side. If you felt like choosing the point 10, 10, we'll say, way over here, that point 10, 10, and I plug that into the original equation, I'm going to get 20 plus 30 is less than or equal to 12, which is saying 50 is smaller than or equal to 12, which is false. So that's showing how that purple point is not a solution, so I should the other side, the opposite side. And those are the steps to graphing inequalities. So I'm going to call that good, and I'll see you tomorrow.